Hello students, welcome back to Physics for All YouTube channel. In today's session, I am going to explain you a very important topic, that is intrinsic concentration in intrinsic semiconductor. This topic is very important for the end semester examination. So without wasting much time, I am going to explain you about calculation of intrinsic carrier concentration in the case of intrinsic semiconductor. Already from the previous slides, I am explained about the definition of intrinsic semiconductor, conductivity of intrinsic semiconductor and doping, then followed by extrinsic semiconductor, which can be derived into two types, N type and P type. To understand all these topics, you can refer my previous concepts by observing my YouTube channel, Physics for All by Dr. M. Reddy Babu. Now today I am going to explain you about derivation of intrinsic carrier concentration in intrinsic semiconductor. For this calculation, I am going to consider an intrinsic semiconductor. Already from the last two classes, I have explained about the derivation of intrinsic semiconductor. Okay. Now we know that in intrinsic semiconductor, always there is equal number of free electrons and holes. In intrinsic semiconductors, it has equal number of free electrons and holes. Okay, this is the first point. Okay, and the second point is these free electrons are available. These free electrons are available in the conduction band, and the holes are in the positive charged carriers which are existing in the holes are present in the valency band. Now to calculate intrinsic carrier concentration in intrinsic semiconductor, I am writing expression for the free electron concentration in the valency conduction band, that can be written in the form of an equation, that is equal to Ne. It represents what the meaning of Ne? Number of free electrons in conduction band. Mathematically, this number can be written as follows: Ne is equal to Nc into exponential of minus of Ec minus Ef divided by KBd. This is a free electron concentration in the conduction band. Okay. Now in this equation, let us know about what is the meaning of each and every part. Okay. Here, where Nc is a conduction band constant, Ec is a conduction band energy, Ef is a Fermi energy. F is a Fermi energy. Then Kb is equal to Boltzmann constant, and finally T is the temperature. So this is a representation of, it is a representation of free electrons, representation of free electrons in the conduction band, that can be written by using the equation, that is Ne is equal to Nc into e power minus of Ec minus Ef by kBt, where Nc is a conduction band constant, Ec is a conduction band energy, Ef is a Fermi energy, Kb is a Boltzmann constant, and T is a temperature. Similarly, the number of holes, which are present in the VB means what? Valency band. The number of holes present in the valency band, mathematically that can be written in the form of one equation. Np is equal to, same expression, Np is equal to Nev into e power of minus Ev, e power of minus once again Np is the number of, what is the meaning of Np? Number of holes in the valency band, and Ne is the number of electrons in the conduction band. Now I am writing in terms of equation. Okay, listen carefully. I am writing equation for the holes in the valency band. Nv is equal to e power minus of Ef minus, here I am writing first Ef minus Ev divided by kBt. This is equation number 2. Now in this equation number 2, where Nv is equal to valency band constant, next Ef is equal to Fermi energy as discussed in the previous, and Ev is equal to valency band energy, then followed by Kb is a Boltzmann constant, and T is applied temperature. Okay, this is about the free electron concentration in the conduction band and hole concentration in the valency band. This can be written using the two expressions. Now equation 1 represents free electron concentration, and equation 2 represents hole concentration. Now we are discussing about the one second. Now we are going to discuss about the density of or concentration of electrons and holes in the intrinsic semiconductor. For this reason, in intrinsic semiconductor always we know that number of electrons is equal to number of holes. Now what we have to do? We can equate first equation and second equation. Once again, instead of equating first equation, second equation, what we will do? Now I am using the one notation that is called as a law of mass action. I am using law of mass action. What is the meaning of law of mass action? I am using the concept of law of mass action. Okay, according to the law of mass action, it indicates that the product of electron concentration and hole concentration is the product of electron concentration and hole concentration is equal to a square of the intrinsic concentration, that is equal to N into P, that is equal to Ni square. Okay. Now in this expression, now we are discussing about the intrinsic semiconductor. It is a intrinsic semiconductor. conductor. Intrinsic semiconductor which contains number of electrons Ne and number of holes Np, both are in equal number. Therefore, what I am going to use in the above equation, in the place of N and in the place of P, I am substituting the above equation. So, what I can use, N into P is equal to Ni into Ni, that is equal to N into P is equal to Ni square. In this equation number 3, where N is equal to number of free electrons in the conduction band and P is equal to number of holes in the valency band. Therefore, I am going to substitute first equation and second equation in the equation number 3. Okay. Now, what is the first equation? N into N means N is equal to, I am going to check the previous equation. You check the previous equation. What is the meaning of N? Number of holes, what is the meaning of N? Number of electrons in the conduction band. That can be written mathematically in the form of Nc into e power minus of Ec minus Ef divided by kBt. This expression into number of P means the number of holes, that it can be written from the equation number 2, that is Nv into e power minus of Ef minus Ev divided by kBt. This is equal to Ni square. This is about, so after substituting the first equation and second equation in the equation number 3, I got this equation. Okay. Now in this equation, I am combining both Nc and Nv. Both are constants only. So I am writing Nc into Nv in one bracket. Then the remaining expression, that is e power of something and e power of this one, I am writing the form of e power of A into, or from the lower classes we can know e power of A into e power of B. What you can write? E power of A plus B. I am using this notation. Okay. As per this notation, I am using e power of, first I am multiplying with minus into Ec minus Ec, minus into Ef minus plus, so plus Ef. Okay. Then I am multiplying with minus here also, minus into Ef minus Ef, then multiply minus into minus Ev, it will become as plus Ev total divided by kBt. This is equal to Ni square. Now without any confusion, all of you listen carefully step by step. Okay. Now in this expression, I am writing same as it is here, Nc into Nv, rewriting the same expression, e power of here plus Ef and minus F is going to cancel. Okay. After cancelling these two terms, what I am writing here, minus Ec plus Ev, minus Ec plus Ev divided by k suffix b into t. This is equal to Ni square. Now in this above equation, I am taking minus as common. So what I can write in this equation, Nc into Nv as it is, then e power, I am bringing minus as outside. So what it will become? Minus Ec. So minus going to outside, so it will become minus Ev divided by kBt. This is equal to Ni square. Now already from this equation, in this equation, Ec is known as conduction band energy, E is known as conduction band energy, and Ev is known as valency band energy. I am subtracting conduction band and valency band. To understand properly, I am drawing this energy band diagram. Okay. Now this is a valency band here. This is a valency band. Okay. And above the valency band, there will observe the conduction band. It is known as conduction band. Okay. Now between this is a conduction band. Okay. And lower one is a valency band. Between the valency band and conduction band, some gap present, small gap present. This gap is called as energy gap. Okay. Now this is a conduction band energy EC and it is a valency band energy EV. I am subtracting EC and EV. So what I will get? Energy gap I will get. Therefore, in the above equation, in the place of EC minus EV, I am using the energy gap. So I am writing the equation. So NC into NV within the bracket as it is, e power of, in the place of EC minus EV, what I am using? Energy gap, that is EG divided by KBT is equal to Ni square. Now what I need in this expression? I need equation for the intrinsic concentration in intrinsic semiconductor. So I need only equation for the Ni. So Ni is equal to, what I am writing here, Nc into Nv whole power of 1 by 2 into e power of minus Eg divided by 2 kBt. This expression I got. Okay. Now in this expression, now we will discuss what is the meaning of each and every term. Okay. In this expression, what is the meaning of Ni? Ni is a intrinsic concentration or density of charge carriers in intrinsic semiconductor. Number 1. Number 2, Nc is a conduction band constant, Nv is a valency band constant, and Eg is a energy gap or simply called as forbidden energy gap. Kb is a Boltzmann constant. T is the applied temperature. Okay. Now from this expression, let us consider this is the equation number 4. Okay. In this equation number 4, now you can observe all the variables and constant. I am going to write here instead of taking another page. I am going to rewrite here. Okay. All of listen carefully. So in this equation number 4, Nc and Nv, Kb are the constants. Therefore, what I can write here? Intrinsic concentration directly proportional to the intrinsic concentration is directly proportional to the function of the energy gap. That is the first one. This is the first one. Okay. And the second one is intrinsic concentration is also depending on the temperature. Second one. Okay. Now the third one is intrinsic concentration is independent. Intrinsic concentration is independent of the Fermi level, which can be represented by the EF. So this is about calculation of intrinsic concentration or density of electrons and holes in intrinsic semiconductor. Mathematical concept, it is completely very important for the examination point of view. Go through these steps carefully. If you have any doubt, refer the presentation once again. Still, if you are having any doubt, then give me in the form of comment. I will explain you in once again. This is about calculation of intrinsic concentration in intrinsic semiconductor. Thank you for watching this presentation. In the upcoming session, I will discuss you about another important concept, that is called as a position of, very important for the examination point of view, that is called as position of Fermi level in the intrinsic semiconductor. For regular updates, subscribe my channel. You will get the notification. Thank you very much for watching this presentation.